So I'm going to actually cover quite a lot in a very short time here. So this is more about the journey than about the details. There's an awful lot of detail in stuff that has gone into this thing called FIBO, which I'll explain about. So I'm going to really cover what was the thinking behind why we did this thing. It's called the Financial Industry Business Ontology, or FIBO. And then some of the things we learned along the way, because it's been very much a journey of discovery. We've heard all about linked data, and this is a data-focused conference, and yet there's a whole science of ontology that goes back to Aristotle that has nothing to do with data, and sometimes there's a kind of uncomfortable relation between the two. And so we've been straddling that relation, and I'll briefly skim over some bits of research that a few of us have been doing over the last couple of years to try and bring together the world of things and the world of strings, as it were. So it's very much a high-level kind of here's what we did kind of thing. So I'd say we'll start with the motivations, and the focus on all this is something we call a concept ontology, and I'll come back to that in a moment. So first of all, let's just look at what the industry was dealing with. In the financial industry, a lot of us have been involved with various data standards and messaging standards for many years. You've got local data stores. I've just put some random pictures of different kinds of schema, so UML and XML and so on. And the problem you have in any big institution, and we're primarily in finance, but this really applies anywhere, is how do you map, is the coupon here the same as interest rate over there, and is the tenor here the same as the tenor there? And for one thing, you've got a lot of very complex point-to-point mapping, which is very expensive. Each time you integrate a new system, you're bringing in a new data source, you've got to do all this point-to-point mapping again. The second thing that's equally important is these big question marks. Once some smart person has done the mapping and moved on, how do you know who thought that interest here meant the same as coupon over there? And were they right? Where's your record of what was the relationships and all that mapping? So for those two reasons, we realized that what the industry needed was a common resource, a common representation of shared business meaning, independent of any of the data. So this is all classic development science, really. You have a conceptual model that's distinct and independent from any logical or physical model. It's not an abstraction out of that, it's some common model, and it's what we call an ontology. And the FIBO initiative, which was headed up by a group called the Enterprise Data Management Council, was to basically do two things: to create this ontology as a common point of reference, so immediately you have one-to-one mapping, and so a lot less mappings and integration and so on. Secondly, you know what it was that somebody thought this field or that tag or that class actually meant in the real world. So we wanted to abstract away from the world of data into the world of real things and have this ontology. But of course, it's no good if it's not validated by business. So we had a multi-year effort. We got loads of folks from all over the financial sector, principally in North America and Europe, but elsewhere as well, taking initial drafts of what we thought the ontology might be. So I took some of these data models and I kind of reverse engineered them into this ontology format, which you heard in the previous talk. An ontology is a formal specification of a conceptualization. So we said, well, here's these data elements. What are the things they're about, the real things? And then presented that to business to validate it. And we did that by expressing it with simple underlying logic. It's a simple subset of logic which can be read by machines and by humans. We had a simple diagrammatic format that allowed us to present it to the humans. We explain it entirely in set theoretic terms and say, is this one of those? And if you have these properties, does that mean you're a member of the set of things which are a credit default swap or something? So that was the broad overview of the FIBO project. So the first thing we thought of was, okay, let's take a look at some of these data models and work out how to turn them into an ontology. The data models are data about something. What is the thing? So you've got financial instruments, commodities, entitlements, events. These are all kinds of things in the financial world. And we said, okay, so let's take an equity instrument. What is an equity? It's a financial instrument setting out a number of terms defining rights and benefits to the holder in relation to holding a portion of equity within an issuing company. Nice simple definition. You've got a word, you've got a definition. First thing we're doing here is we're moving away from words, because as you heard before, words tend to get reused. The same words mean different things, different words mean the same things. We're going to get from words to concepts. So this this word has a nice definition, and the definition sets out a nice simple concept. The word equity might refer to 3 other things, but this is what we mean by it here. So we can take what was written in that definition and just put it in nice simple terms of categories of thing and relationships among those categories of thing. So it's equity security is a kind of financial instrument. It has rights defined in instrument terms in relation to the equity in some company. There it is. We've taken the definition of the thing, taken it out of the world of data and into the world of real things. And so then we're able to build this thing called an ontology, where you have these formal properties and classes and things, and you're defining the real things in the world and the facts about those things. So what we then did, we did it in OWL. This is a picture of this OWL language. We got this hierarchy of classes of thing. We got, everything is a thing ultimately. You have this class thing. That's the universal set of which everything is a member in the world that you're looking at. And then we realized there's a number of common terms, like cash flow terms, like interest accrual, places and time and contracts and so on. So we ended up realizing we needed a very good fundamental set of foundational building blocks. So we built that out. We built it out using the web ontology language, which, as you've seen, is based on subject, verb, object triples. Just to go back a little bit, that previous thing I showed you, I was taking a data element and turning it into a model of the real thing. But just for fun, I also took an existing logical data model from ISO 20022, the thing called the Financial Industry Business Information Model. You can ingest that into OWL. What do you get if you take a logical data model and ingest it into an OWL tool and represent it in OWL? Do you get an ontology? No. You get a logical data model that happens to now be in OWL. Changing the syntax doesn't change the semantics. So be very careful. You'll see a lot of things wandering around out there calling themselves ontologies just because they're a file in OWL. You've got to learn what is it I'm looking at. Am I looking at a logical data model? Am I looking at ontology? Syntax is not semantics. So we developed this, what we call a concept ontology. It's about things, not strings. If you're liable for some, compliance failure, your personnel record doesn't go to jail. You do. So we're modeling the real things in the world here. And we'll come back to data in a while, because you'll see that by focusing on the real things, it raises some interesting challenges. Often you can have whole conversations with people where you think you're talking about the things and they're talking about the data about the things. How do we manage that relationship? So we got what we call the FIBO moment. This is, again, coming back to this notion of concepts. People could argue, and there was a big meeting that Mike Atkin of the EDM Council was at, where they were trying to standardize on some vocabulary or some terminology. Let's all agree to use the same terms. Let's all use the same word equity to mean the same thing each time we use it. Never going to work. Quite aside from the fact that it's expensive to try and make people change all the labels and all the stuff they're doing, it also, if you even look at a very simple amount of philosophy, you soon learn that it just can't be done. But what if we consider the concepts without worrying about the words? So there was this big meeting that Mike Atkin was in, and people were fighting about, we can't change this word, and you've got to use that word, and this term is such and such. He said, well, do we agree about what the concepts are at least? Oh yeah, they all said, yeah, we all agree about the concepts. Right then, let's build something that's about the concepts. So that's what FIBO is about. It was originally called the Semantic Repository. We took all these industry standards. We did these multi-year, week by week subject matter expert reviews. We displayed it all in spreadsheet and in that boxes and lines format. We had a tool we used for it. We brought our theory of meaning in from the Semantic Web. We could express it in RDF and OWL as well as in the tool that provided those views. And that was the thing we did for years and years. Here's what's the scope of it. The core of it is what we call the contract ontologies, so securities, derivatives. Every financial instrument is basically a contract at the end of the day. Then we've got some more foundational stuff, business entities, common business and commerce terms, indices, and some high-level abstractions, these building blocks like places and times and events and things, and a scientific thing called an upper ontology, which you don't need to worry about. And then coming up in the future, we've done a lot of the work on this already, got very detailed work on pricing and analytics and things that vary with time. The ontological nature of time and temporality is quite a difficult one, so we've been holding that back for some research on that. And likewise, things like process terms like issuance and so on. What we don't have, which is needed for most financial reports as well, is stuff about the bank's own position in things. So portfolios and holdings, positions, exposures. The building blocks for that are all there in foundations, and some of them are used in tradable fund instruments and so on. So that's the overall, that's what's in FIBO. You'll see it's very securities focused, very, what do you call it, kind of wholesale markets focused. We don't really have much retail stuff apart from loans. We're starting to open out more retail stuff. But because of these high-level abstractions, you could also apply some of these concepts into retail banking and insurance and so on. Now, we said we wanted to deal with concepts, things not strings. We said we wanted something that's framed in basic logic so that humans and machines can understand it the same. We said that the business stakeholders have to understand it and validate it. We didn't say anything about data, and we didn't say anything about what we would use. We experimented with various things. We ended up with OWL, as you saw. The thing with OWL is that most of the people that use OWL are doing something very different to what we were doing. We're building a common ontology using formal logic to present the language of meaning. There's a lot of science from the discipline called applied ontology going into there. But a lot of OWL applications are very data focused. They have richer internal logic to create little standalone use case specific ontologies. And those are fine as they go. And there's a lot of design rules that you would follow if you're doing a standalone ontology that you would absolutely not follow if you're doing a common language across a whole industry or even a whole company. So a lot of the stuff that the Semantic Web folks would instinctively do were exactly the wrong thing for FIBO. And a lot of the things that we did in FIBO to capture the concepts across the whole industry with very deep taxonomies of fundamental semantic building blocks were very much the wrong thing if you're doing a standalone Semantic Web application. So we needed to start to tease out this difference and figure out how do we get from a common industry language to these OWL application ontologies that let you run lots more complex reasoning and inference processing and so on, and add rules to them and all the rest of it. So we created a new ecosystem over the last 4 years. We got a common repository. We deliver a thing called vocabulary, which is in the SCOS language. That's another RDF dialect, specifically for vocabulary. We got a new UML dialect called SIMF, which is a business-facing conceptual model language that runs in UML. We've got a good relationship with schema.org. We're working through the object management group with these UML-based things. And all of that is derived from the same underlying ontology. So our system of record now is RDF OWL. Previously we had that other repository that generated OWL. Now we have OWL as a system of record. But that means that some of the way that this is done is a very OWL-y kind of way. So here's a good example of what you do with that OWL application kind of thing. You've got, this is a picture of an interest rate swap. You've got the different legs, you've got the different parties. Notice this is very data focused. So obviously you've got things like notional amount and fixed rate, they're numbers and percentages anyway. For your business entities, we kind of use things like the LEI identifier for them. So there's the LEI there identifying the entity. So it starts to link into the data itself and links into things like linked data and so on. And you can reason on this, you can look at this and say, oh yeah, this is a fixed float interest rate swap. The two currencies are the same, so it's a vanilla interest rate swap. If the currencies were different, it would be a cross-country currency swap and so on. Now, there's a couple of things in the world of OWL, and here I'm just going to really skim over this very quickly in this last 5 minutes. Some of the things you might see in OWL in an application that would be wrong for a common language like FIBO is having properties with no domain and range. So in this UML-based format, if a property has no domain and range, we just simply attach it to the class called thing. That's the universal class of which everything is a member. Now, if you're doing a standalone OWL application, it actually makes sense to have no domain and range for your properties because you want to be able to reuse them almost as if they're just a word that can be used in different ways. It means you can do a standalone ontology where you can reuse a lot of stuff. You don't need all these abstractions. If you're doing a common language, the example Tara gave is a really good one. If a project has a project manager, that's always and only ever going to be a property of a project. So why would you not tie it down to project? But in standalone OWL applications, this is a very common pattern. So we looked at it and thought, well, it can't be wrong, but it's just not what we want. How do we put some science around this? And we realized very briefly there's two approaches to meaning. I'll put them in a very rough shorthand as kind of Rosetta Stone versus Mayan language. Rosetta Stone, you ground the meaning from one language to understand things in another. The Mayan stones, there's no language to compare it with. You had to work out from internal consistency what things meant. So in the traditional semantic web approach, you actually have a network of things in the world. You have a network of classes and properties which matches that, and you put enough detail to ensure that that little standalone local network accurately corresponds to the things in the world. There's no grounding of the meaning. Whereas what we call foundational semantics, which is what we used for the early parts of FIBO, again, it's the directed graph. You've got classes and properties, but we use this Earth symbol here, which confuses some of the ontologists, but given where we are, none of you should have any problem with this. You ground the meaning at certain points. You have fundamental primitives like social construct or place or some fundamentally primitive concept, the meaning of which is grounded outside the model in some definition, and you say, right, let's build up from these primitive concepts to the whole thing, which is instinctively what most of us doing conceptual ontologies would do. Because only when looking at what the owl guys do that we realised that we had to articulate the difference between these two styles of meaning. So foundational semantics, you ground certain concepts outside the ontology. And notice here we're talking about real things in the world, like social constructs, commitments. A lot of these don't exist in data. They're the real things. To a data person, a social construct is terribly abstract and airy-fairy and not real. Actually, that's the real thing. The data is the abstract thing. Internal correspondence semantics, you tend to have a lot more restrictions in amongst properties and a lot more restrictions and properties going around in circles to try and create a graph which, when you close that graph and reason over it, the whole graph has meaning in it. It doesn't adhere at any particular point. So a couple of other interesting issues with OWL. We're using OWL to do a concept ontology. That's a conceptual model. It's not a logical model. And yet it has data types. And data types represent a commitment to data. So we had to refine our principles. And here, I'm not going to cover this in detail because we're out of time, but I just wanted to give you a sense of it. A bunch of us kind of stepped away and created a little brainstorming huddle, and we looked at the different aspects of the problem we're looking at. We realized that there are different dimensions to a model, that people will often say the expressive power of a language means that it is more semantic or less semantic. Actually, the semantics is about what do things mean, how you use it, if it's logical or physical, and what's the formalisms such as UML or first-order logic are dimensionally distinct. And one kind of model, the one that the ontology is a semantic model. It's not a logical data model, but it's at that business level. This is the Zachman framework. So it's not an abstract model of the solution, like some people would use the word conceptual model for. It's a concrete model of the problem. So I haven't got time to go into this, but I just want to let you know that we did a whole lot of analysis on that. What's it a model of? What we call the semiotics, or the commitment of each element in the model. Does it represent some piece of data, or does it represent some real thing? And so we go back to a thing called the semantic triangle. We analyze the notion of a concept. A concept has both an intention and an extension. There's a lot of science out there and a lot of academics arguing to and fro about the nature of some of these things. But we said, just from a simple engineering point of view, how do we deal with this? Our model, what we're calling an ontology, is really a model of what's called the intentions. Note that's intention with an S, not a T. That is the thing, the logical description of something. We don't care about the extensions particularly. You could have many extensions, in different possible worlds. What we're interested in focusing on is what is the concept. And then you can go from concept to data. And with data, this is where it gets really interesting. We have what's called the A box and the T box. A box is the individual assertions, and we have these extensions of the intention. This is often different. There's what we call a delta data, a distance between a concept like commitment and a data element. Now this can be very, very little. You can have an ontology where we're creating data for real world things because they weren't already there in data sources, or you have, if I go back, an ontology which looks at available data and reasons over that, and you work out the relationship between that and the real thing. So you have data that's surrogates for real things in the world. So that gets you from things like legal capabilities and rights and things to data surrogates such as licenses, identifiers, and so on. So FIBO's there, edmcouncil.org/FIBO. There's two parts of it. And this is where everything I've just told you to be aware of, you need to look at, because we have two styles in FIBO. We've got the foundational development FIBO, and we've got a smaller amount of production stuff that's optimized for semantic web applications. You need to really look at that theory that we built to work out which of those ontologies to use for what. So, very short time for questions because we need to go on to the other speaker. No time for questions. Splendid. Yeah.